Okay, yeah, welcome back, everybody. I'm really excited to be here. I'm happy that I made the trip this weekend, and I'm now able to give this lecture from now on here in person. Thank you for this great setup with the video and everything. It is actually, after seeing this only through Zoom for the last, what is it, almost 2 months, this is really impressive also here. Okay, so I will simply, I was stopped last time. I'll remind you what I was talking about and continue a little bit more about what I called Miller's conjecture. And then I talk also, so probably I've only talked about in the situation of expansions of the field, but I will do so, talk a little bit also today, and maybe that's the only time I will do this, or maybe on Monday next week, depending on whether I finish today, about expansion of the real group. But really I care in this lecture about the field, but there are certain things from a larger perspective that I want to say about the field. So start in the middle, but I start in the middle. So again, let R be an expansion of the real field. And again, I point out that I'm going to talk about expansions or reducts, and it's always in a kind of, not in a syntactical sense, and more than the sense of whether or not the expansion defines more or less definable sets. And so we had last time this Miller's conjecture. And Miller's conjecture, we had this in 2 statements. And the one statement that I will now going to give is that suppose R be an expansion, again, be, suppose that R, how do I want to say it? Like this. Suppose R does not define the integers, or sometimes I will write n, that's really just the same, or for in this case, then the open core, a second, what this is in a second, is noiseless. So the open core was a reduct of R by all definable open sets. So if for every open set, you add a new predicate to the language if you want over the real field, but just for the open sets. And then you'd look at the structure this generates. And noiseless was that every unary definable set either has interior, or is nowhere dense. And what I pointed out last time was that this kind of having either interior or nowhere dense, it truly holds for open sets. It also holds for closed sets. And essentially the question here is that if you know this for open and closed sets, can you get this for every definable set in the open core? So everything that is generated by this. And what I want to talk about first, and it's like somehow where I stopped last time, is I want to talk a little bit about the progress. So what kind, do we have any kind of results in this direction? Okay. Okay, and so the first result I want to state is the following. So if this, I think my numbering is 1.2 and 1.12. So that's a result of mine that I actually did here at the Fields Institute 12 years ago. And this is the idea that, so let's suppose you have a set D and let B closed and discrete. Okay. And definable, of course, definable, closed and discrete set. So of course, closed and discrete is always in the usual topology of reals. And so now what we also suppose and F is a definable function definable function on R such that f of d to the n is somewhere dense. Okay, so that's still the assumptions. But I want to say a few words of it. So definable, of course, is now supposed always with respect to the fixed expansion of the real field that we fixed. And so now suppose this we have a definable function that maps this maybe a power of the discrete set to somewhere dense. This f, I mean, this f could be semi-algebraic or something like this, but per se, this could be any defined, just say it's a definable function in the structure. Then the conclusion is then this structure defines. Okay, so why is this somehow first evidence towards Miller's conjecture? Because what this so I give you a closed set, and if I can transform this with a definable function to something somewhere dense, so something, I mean, surely if D is closed and discrete, then it's countable. So the image of this is countable as well. So that means that it's codense. So this f of d here, this f of d to the n, okay, if you throw away didn't you, if it neither has interior nor is nowhere dense. So that means that this f of d is a counterexample to being noiseless. So if you can generate noise just from a definable function from some discrete set, then you already define the integers. So something like this cannot happen in the structure that doesn't define the integers. To give you an example of how this kind of looks like, and that this is something rather natural, let me do here one example. And essentially, this is the example where this theorem was produced for. And this is what I mean, if you have seen Chris' lecture, you already know that. So you take the real field, sorry, I gave this a name, so let's keep that name. And you add to this 2 to the z union 3 to the z. Then this is, well, it's not close, but if, I do 2 to the n, 3 to the n. Then this is a closed and discrete set. And then you know that the following function is, of course, definable in there. Let's write it like that it's a semi-algebraic function to R. It simply maps xy to x divided by y. Okay. And so now if you restrict this function f to this, so now note that if you restrict this to this, so if you look at the image of the union of this discrete set, then this is somewhere dense. Okay. So this is that's the idea. That's a typical example of something where you have something discrete, but it's not discrete enough. It's not discrete enough such that if you have still semi-algebraic functions, that then kind of collapse it to something somewhere dense. Okay. Okay, so this can be strengthened to something that is even more, I think, more obviously a step into in the direction of Miller's conjecture. And for that, I have to introduce some notation, again, from an earlier paper from Patrick and Chris. And so this is now, there's a name 113. What I want to define is now these sigma sets. So again, this notion is from this fundamental paper of Chris and Patrick, I think 99, where they study the o-minimal open cores. And so the definition is the following. We say that E subset of R to the n is the sigma. The sigma here is really this will be an analog of the notion from descriptive set theory. This is called F sigma. So F sigma sets from descriptive set theory, from mathematics in general, are countable union of compact sets. And so now we want to do a definable analog of that. So this E is the sigma if there is a definable family, a definable set X subset should be R times R to the n, such that, well, the union of the fibers. So this XR is supposed to be all the elements. So this is element above E. So this XR is really just all the pairs Rx, such well, in this case just all the x's, such that Rx is an X. Okay, so you want to have that E is a union of these fibers, but you want that the fibers have certain properties. First of all, this is maybe the main thing, is you want to have that this is compact. And remember that for F sigma sets, this always have to be a countable union. So you have to some kind of add a definable analog of countability. And the analog we put on there is that we asked this family here in R to be increasing. So or decreasing, whatever you prefer. It doesn't matter. Right. Okay. So you can check. That's an exercise. You can check that every d sigma set is F sigma, but there are in principle many F sigma sets that are not d sigma. Yes, please. Oh yeah, okay. So yes, but this can mean yes. Yes, would you have a count that should be the same? Yes, because yeah, you're right. Okay. You have, so the one reason why we don't say definable F sigma is because it's, I mean, it's not so obvious what that would mean. I mean, you could theoretically define something like, okay, this would have to be a countable union of definable sets or something like this, or define a countable union of in a definable family or something like. So that's why I think Chris and Patrick introduced the name, the different name, and didn't call it definable F sigma. Okay. One thing I do want to point out, and maybe write this over here, let's start here, is a remark here. When working over the field, and in the early paper, Chris and Patrick already showed that a set is d sigma if and only if it is a projection of a closed set. So E is the projection of a definable closed set F. So if you want this to be an R to the n, in this case, this would be the projection onto the closed onto the last n coordinate. Okay, so in particular, I stated this kind of remark in order to tell you that if you have a d sigma set, then it is also in the open core, because you have this closed set, and if you this is structure, so structures so defined sets are closed in a projection, so the set E is again d sigma set. All right, and so I think one of the things, where do I still have it? Miller's conjecture. So I said that we want to have Miller's conjecture for stating that the open core is noiseless. So we want to have that every set in the open core either has interiors or dense. We know it for closed sets, and somehow the next step here is then, of course, the sigma. I mean, if you think about in terms of the Borel hierarchy, then of course you start with closed sets and open sets, and the next thing is you do F sigma, then the complement is G delta, and so on. But the next step is really is F sigma. So in this case, it's D sigma. And for these, we do have, that's what I want to state here, we do have Miller's conjecture for these sets. So this is now Miller's conjecture for the sigma sets, but I want to state this slightly differently, or call this slightly differently. I like to call this what I call the strong Baire category theorem. And I'll tell you why in a second. So suppose that the expansion we're working with R does not define Z, then every D sigma sets and each either has interior or there's no limit. Okay, so a couple of things. First off, so why is it called the strong Baire category theorem? Because you can show that the usual Baire category theorem will say that every F sigma set either has interior or is meager. Okay, so this is I mean, if you have an F sigma set, then either if it's either is an interior, then you what do I say? If it doesn't have interior, then it's a countable union of no sets. So that's what's called meager. But in this kind of setting, that's why I call this a strong category theorem. And this is really the crucial result, is that you know that not only is this if it doesn't have interior, you don't only know that it's small in the meager sense in the descriptive set theory, but you really know that it's small in a topological sense. I mean, so it's really there's lots of space there. This theorem here, this is, I mean, the proof I will not do, or I might do later, but definitely not now. Uses this proof uses and quite heavily this result here. So it's essentially this kind of the first generalization of this result to the sigma sets. This was first proven by actually by Anton Giulio von Arcero. He used this kind of, after I proved this result, he really proved this in one of his preprints. That preprint never appeared. If you want to put the first where this really appeared published was in a joint paper with me, but I think Anton Giulio was, I think, the first one who proved that. Okay, so this is kind of the first step, and really I think this is for a set theorist, this must be really a dream theorem, because it would be, I think, as a descriptive set theory, you would always love that small really also means small in a clear geometric way, but in general this is of course false. And for example, the rational numbers here are the sigma set, and of course they are somewhere dense and don't have interior. Okay, so then the next step, and this is we'll talk about this much more later on, but I want to state the result now, is so you have this minimality for the sigma sets, and now you want to somehow talk about geometric consequences. The overall thing that we're going for, and that I hope to reach at some point, would be some kind of cell decomposition theorem, so some kind of big, really clear geometric understanding. The best thing we have, and Chris has used that a couple of times, but I'll state it now again, is that we at least understand the metric and topological dimensions of these sigma sets. So let me state here, state this here, so that this is 1, this should be 115, is the following result that makes this kind of strong back category theorem into something even more geometric. So let E now be a subset of R to the N be d sigma. Okay, then can you see this? You probably have to stop here, otherwise. Then we'll define both of this in a second. Then the dimension, the topological dimension, or even just the kind of the naive dimension that from o-minimality, this is equal to the Asura dimension. So that dimension here, maybe I write this here. So this is, I will not make the full statement here, but the kind of this dimension on the left-hand side is supposed to be a topological dimension. So if you want to take this, any of the, so the Lebesgue's covering dimension or whatever, all these kind of equivalent topological notions of or inductive dimension, all these the topological notions of dimension coincide for the reals. So take whichever you like. And if you have never thought about this kind of dimension, then you can really even use the one that you hopefully have seen in the o-minimality course, which is that the dimension of M is a maximum, dimension of E is a maximum M in N, such that there is a projection, coordinate projection from Rn to Rm, such that projection of E has interior. I will define Asura dimension one more time in just a second. But one thing that is important now in regard to this kind of theorem is that already I want to remark this here. The Asura dimension of E is equal to the Asura dimension of the closure. That is, of course, not true for topological dimension. For example, the dimension of the rationals in a topological sense is, of course, 0, but the closure, so note, for example, if you have the rationals, then the dimension of this is not equal to the dimension. So for any dense, for any dense and codense. Okay, so in particular, okay, let's see. Yeah, just like sorry, so in particular the dimension of E is equal to the dimension, so the Asura dimension of its closure. And so if the Asura dimension is smaller than N, then the topological, sorry, if the, sorry, if so sorry, this way around. So if E, I have it, doesn't have interior, then at least in this case, then dimension of E is smaller n. So in the case yes, if E doesn't have interior, then the dimension, topological dimension is smaller than n. So if you are if n equals 1, then in this case, if the E doesn't have interior, then the dimension of E is 0. Okay. And so that then means then the Asura dimension is also 0 by the result. And now you have that the Asura dimension is 0. And that then gives you that the set is nowhere dense. So then, since the dimension of A is the Asura dimension of E is equal to the closure, this gives us E is nowhere dense. So this gives you here a strengthening, so in some sense, a very strengthening of this kind of bare category theorem. No, but then you don't have 0 here. I mean, if you this could be then it's smaller than n, and you would just have that, but this works there. Okay. So that's what I wanted to say here. I wanted to briefly say what this kind of Asura dimension actually is, because I think it's important to get a little feeling for what this is. One thing that I don't want to talk too much about this is that one important feature of this Asura dimension, I'm pretty sure Chris said this a couple of times, is that the Asura dimension is somehow the largest the largest of all these metric dimensions. So if you have heard about Hausdorff dimension, you've heard about Minkowski dimension, about all these kind of notions of dimension coming from metric geometry, then they're all bounded above by the Asura dimension, and they're all bounded below by the topological dimension. So if we can prove that the topological dimension and the Asura dimension coincide, then this really gives you that all these dimensions have to coincide. So in this case, really, what we're showing here is essentially that all kind of used notions of dimension coincide for this set. It would actually be really interesting to see and look at this kind of proof and check whether there's kind of can you make this argument in some sense precise, so can you axiomatize the properties of the metric geometries or dimension that you want, such that you can show that this actually is the largest dimension you actually would want to consider, or maybe there are other metric dimensions that you consider that are even bigger. So to make this kind of naive or this kind of practical statement that this is the largest dimension, precise in a more foundational way. Okay, but I still wanted to say something about metric dimensions. So let's do this 1.6. And so the one dimension I actually will define first is the Minkowski dimension. So that E to be a subset of R to the N, I will say what the Minkowski dimension is, and then I will give the definition of the Asura dimension, but really just kind of, if you understand Minkowski dimension, that is perfectly enough. So how do you do Minkowski dimension? Is really counting boxes and that you needed to cover the set E, and then see how the growth rate of the number of boxes, what the growth rate of this numbers of boxes is as you go to make the boxes smaller and smaller. So we define this N for the set E and the real number R. We define NER as a number of boxes you need of radius, which how far you can see radius r needed to cover E. And then the idea, really the idea, I'll make this precise in the next part, is that you want to define the dimension as follows. So suppose, it's not always the case, as r goes to 0, this is roughly c, some constant r, and then to the minus d. And this d here, this is the Minkowski dimension. Okay. Of course, what happens is that of course, that you will not always find this kind of constant and this d such that this is the growth rate, but rather so you have to take a lim sup or lim int. And so then really, okay, this I always really have to look up because I get this wrong with all the logs. So the upper Minkowski dimension so usually written like this of E is now the lim sup as r goes to 0 of the log. And this part I always remember, and then log 1/2. So put it in, it's 1/2. So this is the upper Minkowski dimension. If you want to do the lower Minkowski dimension, and you do the same thing, and you just replace a lim sup by lim int. And there should be an E. Okay, and so if they coincide, if they happen to coincide, then this is actually what you want. And so you define the Minkowski dimension simply if they happen to be only if those two have to be equal, and then that is a Minkowski dimension. Otherwise, it's not defined. Okay. Okay, any questions about this? So the Asura dimension, this is really for all intents and purposes, at least for me, is always is a uniform version of the Minkowski dimension. That's all you know about Asura dimension. That's really more than enough, but I will still give you a formal definition so that you see at least how it is uniform. So the Asura dimension is what I now call dim A of E is now the infimum over all, I have to get this right, alphas such that there are constant C and rows such that we write it down, and then I will say what this means. So it's the infimum of the supremum of keep the same. That should be a big R, I think. Like the ER is smaller than C Okay, sorry. So what you do is, this is a uniform version that you look, that's a Minkowski dimension kind of is kind of a global thing, right? I mean, it looks everywhere at the set. The Asura dimension says that you have to do it around every point, and not only at every point, you also kind of look at this, you zoom in on that point. So here you think of this as, you look at the ball of radius r around point x intersected with E, so you localize it, and then you scale up this ball by the multiple of r, so it becomes bigger, and then you use this thing r here to cover it. So that's the kind of locality of this. Okay. Okay. So that's the kind of what I wanted to say today about this Minkowski dimension and this Asura dimension and the equality. So this is kind of the first step, or the biggest advance we have towards Miller's conjecture. And so far, it's really really about understanding the size of sets. It's not, we don't have yet any kind of good control that is comparable to cell decomposition statements in o-minimal structures. But that's the kind of the direction we're trying to get. Okay. Yeah, go until 12, is that right? 12? Yeah. Okay, so now I want to do this part over talking about what this means all in expansions of the additive group. So now this is some of the second section, and this will not be too long, but I think it's important for this kind of, if you see this a little bit more as a model theorist, less as a geometer, to see how this kind of connect, how this generalizes, and it's actually really nicely classifies the expansion of the additive group. So for this section, and for this section only, I do want to talk here about really just expansions. And then I really need to add order here for expansions of the additive group. Okay. And so here I really want to talk a bit more about okay, where do the complexity comes from? So the why is it so crucial, or where does the complexity comes from when we have something that maps something discrete to somewhat dense? And so this we really now understand quite a bit better than we used to. And the key definition for this, what we have to discuss here, is what we now call dense omega orders. And so for that, I really just want to say what the omega order is. So we say that in this structure R, that this is an omega order if it is omega order if, well, two things. First of all, of course, this order here is maybe different symbol is definable and has order type type omega. So order type omega really just means that this order is isomorph as an order to the naturals with the usual order. Oh, and this should be at any order. Oh, okay, so order type is fine. Okay, now the crucial thing is, I mean, there are many definable, many nice model theoretic structures that define omega order. I mean, these kind of sets. I mean, for example, if you take, Chris, we spoke about this, take the reals with 2 to the n, then I mean 2 to the n obviously has order type omega. So we know many nice examples of that. The complication arises, and this is really kind of the key insight, is when this omega order is dense. So we say X is a dense omega order if it is this an omega order and dense in some interval. So in particular, what this means is that you want that the X is a subset of the reals, and we say that this is a dense omega order if it's a dense omega order and it's dense in some interval. Maybe we should have called it somewhere dense, but this is easier to say. Okay, and now I want to give you here a few examples. So in particular, I want to show that the example. So we have this theorem which says that if you have a discrete set and that's mapped to somewhere dense, that in this case we have a dense omega order, and this is a very, very natural one. So first of all, maybe do this example here first. I'll leave this as an exercise. Let E be closed and discrete and infinite. Then E is omega orderable. Let me say what I mean by that. So that means I can define a definable order on E such that this becomes omega orderable. And so so in this case it's particularly easy. In this case, the order is really just the usual order. Okay. For example, the integers would be such a set. So, okay. And so now the one thing I want to do is to make a couple of really very easy observations. And in particular, so maybe let's call this a lemma. Let D be an omega. Give the name to an order. Be an omega order. Then then D to the n is also omega orderable, so that there's a definable order on D to the n such that this is orderable. You have to be a tiny bit careful here. I mean, maybe the simplest thing you would do is you would simply, or would hope, to take the lexicographic order. But in the kind of the lexicographic order, that there's no hope that this should be an omega order. I mean, for example, take the naturals and take n to the n, then this is clearly not order isomorphic with this order. So what you do instead is the following. So you have to adjust this order, and so what you do for that is so define maybe maximum, define a function maximum with respect to this order, which in this sense a tuple to the maximum of its coordinates. So if you have x1 to xn here, then this sends it to the maximum with respect to this order of this set here. because you know that with respect to this order, D is order isomorphic to the naturals with the usual ordering, you get that this maximum always exists because it's a linear order. And so then what you do, and what you now define, so now you have two element X and Y in, what was the name I want to give you this order? I should give it N and Y. So this is both in D to the N. Then what I want to do is I will say if this is smaller, if either the max of X is smaller than the max of Y, or if they are equal, it should be, or the max is actually equal, then what I do, now I can use a lexicographic order. So that means, I mean, because there are only finitely many elements now that have in front of it, you know, so now you like, how do I call this, maybe X lax. And then you can check that this indeed gives you a dense omega order. Okay, and now I'm almost done. Maybe I'll give you here as an exercise. Okay. So this is one way this is closed under if you have an omega order, you can get another one. Another way is to let f be a definable function. Doesn't matter where it so from D to the N. Then either f of D is finite, or f of D is omega orderable. I leave this as an exercise. This is really very, very easy to check because you simply, I mean, simply pull it back. That's the idea, and compare it. Okay, and so now then what you get is that this is the last thing I'm going to say today. So now suppose you have you're in the setting of the, so you have a closed and discrete set. And let F, maybe I should keep the same letter, D be closed and discrete, be definable such that f of D to the N is somewhere dense. So then we know by 2.2, we know that D is omega orderable, that's by the usual order. And then by this exercise here, so first by lemma 2.3, we know that D to the N is omega orderable. And then you apply this exercise and you get that the image is omega orderable. So this here, so thus f D to the N is a dense omega order. Okay. And so the result I said at the beginning, and I'll stop, we stated that in this setting here, if you have such a map that maps to somewhere dense, then you always define the integers over the real field. And then what is true actually is that whenever you have a dense omega order and you work with the real field, then you define the integers. And I talk a little bit about this and next time. On Friday it will be Chris, and I will do then Monday again. Yeah. Any questions?
Dense in this context means like the order is a dense order, not that it's dense somewhere.
No, the dense really means that so there are two different orders. There's the order that is on D, this kind of this tilde here, this order,
yeah.
And so that has order type omega, while the underlying set X is dense in the usual order topology on R.
Okay.
So I mean, in some sense, you could really just say you have a structure with two orders on it. One it's the order type omega, and then the other type it's order isomorphic to the reals or to the Russian.